Here is a rather tricky question involving SHM for HL only, and we have a mass on a spring. Mass, Einstein in this case, weighs 120 grams and it's suspended from a vertical spring of spring constant, which is K, of 7.4 newtons per meter. The mass of the spring you can ignore. Here is the full question, so probably take at least 10 minutes to do if you get it right the first time and everything's going well. I'm going to go over the solution, so if you want to try it, press pause, read the graph carefully, read the questions carefully, and see if you can solve questions A through F. So if you want to try it, pause now. Otherwise, here's the solutions. Calculate the elastic potential energy for the equilibrium position. So, elastic potential energy is half kx squared from the spring, and it's derived from Hooke's law, which is F equals kx. Negative just indicates that it's losing elasticity. You're going to lose elastic potential energy. So, first of all, we need to figure out, well, how much is it extended by when the mass is on it. So, using the formula for weight, mass times gravitational field strength of Earth, which is 9.8, that gives us the force, because this weight is going to be giving us this force. And rearranging Hooke's law to find x here, down at the bottom, gives us an extension of 15.9 centimeters or 0.159 meters. When we throw that into our first equation for elastic potential energy, that gives us 9.3 times 10 to the minus 2 joules as the answer for A. State and explain the direction of motion for the mass. Well, right at the top here, you've got maximum extension, the most elastic potential energy you're going to have. So if it's losing that energy at 0.2 seconds, the spring is getting shorter. So if the spring is contracting, extension is decreasing. So if the spring is getting shorter, it must be moving upwards. Pretty straightforward. We've gone from nothing but elastic potential energy right up at the top to, as the spring contracts and Einstein moves up the way, he would lose elastic potential energy until he gets to the top of his peak, and that would have max gravitational potential energy, and obviously he had to move in between those points. So the answer is elastic is transferred into kinetic and gravitational potential energy. Right, now in part A of this problem, we found out that at equilibrium we had 9.3 times 10 to the minus 2 joules, okay, which is about on the graph about maybe 0.18 seconds, something like that. So what we need to do is use the elastic potential energy for the minimum, which is right down at the bottom here. You can read it off. And if you can figure out the difference in extensions between those two amounts of energy, between equilibrium energy and elastic potential energy at its minimum, then you'll find the extensions. So if we work out based on the graph, the extension there, that gives us 0.052 meters, and if we use the difference in the two numbers for extension there, that gives us an extension of 0.107 meters, which will be equal to the amplitude. So to recap, we already had the difference in elastic potential energy at equilibrium, or should I say the elastic P stored at equilibrium, and from that we got the extension in part A. And then if we can use the minimum elastic potential energy, that will give us a new distance which will be at its maximum amplitude. We can figure out the difference in that based on the difference between the two extensions. Now we have to calculate the maximum speed of the mass, and it's worth bearing in mind there's a lot of similarities between the mathematics of angular motion and SHM. So that's sometimes why angular velocity is called angular frequency. So here we can work out that angular velocity, even though it's a mass bouncing up and down, the sort of phase relationship is cyclical. That gives us 7.85 radians per second. From there, we can actually use this equation, which we often use for rotating objects and linear velocity at a point from the radius, but we can use it also to work out the maximum radius within the phase of an SHM object. So it gives us a maximum velocity of 0.83 meters per second. Next up, determining the kinetic energy of the mass at 0.15 seconds. We can use this equation here. Now remember, calculator in radians for this, but if you're going to do vectors afterwards, set it back to degrees. So make sure your calculator is in radians. We've already worked out the angular velocity and the displacement. The phase difference here, because the phase in all these equations is calculated as difference from a sine wave, it has the amplitude starting at 0 at the equilibrium point. Okay, so the phase difference here, because it's at maximum, okay, so Einstein starts at his maximum potential energy. So the phase difference there requires that it's going to be pi over 2 radians difference, which is what we have in the phi as the equation. So it's not starting at 0, Einstein's starting at maximum amplitude. That gives him a velocity at 0.015 seconds of 0.767 meters per second. Now throwing that into the kinetic energy equation with the given mass gives us a kinetic energy of 3.5 times 10 to the minus 2 joules. There we go.